Good morning, everyone. So this is the third lecture of chapter 8. So today we are going to cover section 8.3 and 8.5 of your book, and we'll talk about wedges and flat belts. Okay, so let's start. Now let's talk about the something about wedges. So we all know what is a wedge, right? So this guy here, this is a wedge, right? So wedges are used to adjust the elevation or provide stability for heavy objects such as this large steel pipe, right? It's also used to lift the heavy objects, right? So to adjust the elevation, provide stability, or to lift heavy objects, we use these kind of wedges. Okay, so something about belts. We know we have so many belts in our car, right? We have timing belt, we have other kind of belts. So belts are used for transmitting the torque developed by a motor to a wheel attached to a pump, fan, or blower, right? So in this picture, you can see that this is the belt. This belt is going like this, and this is transmitting the torque developed by this motor to this wheel. Okay, so this is our today's topic, wedges and flat belts. Okay, now let's talk about wedge first. So we know that we need to analyze any system, right? So why do we analyze? Because we want to know what are the forces acting on the system, and we can find out the unknowns, right? So the same we would do with the analysis of a wedge. Okay, so let's talk about a wedge a little more. A wedge is a simple machine in which a small force P is used to lift a large weight W, right? So on the left side, you can see this picture where this is the wedge, this guy, this is your wedge, and this wedge is being used to lift this weight W, right? So now this force P is applied on this wedge towards the positive X direction to lift this weight W, right? So that's how the wedge works. Okay, now to determine the force required to push the wedge in or out, it is necessary to draw the free body diagrams of the wedge and the object on top of it. Okay, so basically in these kind of forms we need two free body diagrams, right? One of the wedge itself and one of the other object which is being lifted, right? So in this case we need the free body diagram of this guy, the wedge, and this box, right? So we need two free body diagrams to solve this kind of system. Okay, so now if you look down at this diagram, this one, what can you see? So this is the diagram of the free body diagram of the wedge. Okay, because it's easier to start with the free body diagram of the wedge because we know the direction of its motion, right? Because we know the direction of this force P, so we know that the wedge is moving in this direction, positive X direction, right? So that's why it's easier to start with the free body diagram of the wedge. Okay, now we know this force P. Okay, maybe we know the magnitude, or maybe it's unknown and we need to find it, but at least we know the direction of this force. Okay, so we know that this wedge is moving towards the right, right? So where the friction force would act, what will be the direction of the friction force, right? So we have two friction forces acting on this wedge, this guy F1 and this guy F2. Okay, so we all have gone through the practice problems and the concepts of the dry friction, and we know that the friction acts always opposite to the applied force or opposite to the direction of motion. So direction of motion is positive x direction. So in that case, the friction force would act in the negative x direction, right? So F1 is acting in this direction. This is direction of F1. This is direction of F2, right? Now the bottom of this wedge is plane, right? So that's why the F1 is also parallel to the surface, okay? So that's in negative x direction. Now with regards to F2, it will be parallel to the surface of the top surface of the wedge, which is inclined at an angle theta, right? So that's why we can see F2, it's not purely in the negative x direction, it's inclined at an angle of theta, right? So it will always be parallel to the surface, okay? Then we have these two normal forces, N1 and N2, right? So we know that the normal force will act on the surface perpendicular to the direction of the surface. Okay, so we have these two normal forces, N1 and N2, acting on the wedge. Okay, so that's how we are done with the free body diagram of this wedge. Now there are some key points which we need to keep in mind. We already discussed about these, but let's go over these again. Friction forces are always in the direction opposite to the motion of the wedge. Okay, so we already talked about this, that how we apply the friction forces on the wedge. Okay, next, friction forces are along the contacting surfaces. Okay, so we already talked about this, that the friction forces will be along the contacting surface. So in this case, F1 and F2. Next, the normal forces are perpendicular to the contacting surfaces. So we already discussed this about N1 and N2, that these are the normal forces and they are perpendicular to the contacting surfaces. Okay, so that's how these were the key points, and we are done with the free body diagram of the wedge. So next is the free body diagram of the weight or the block which is being lifted, right? So this is the free body diagram of that block on top of the wedge. Okay, so there are some key points. Let's have a look at these key points. At the contacting surfaces between the wedge and the object, the forces are equal in magnitude and opposite in direction to those on the wedge, right? So that's why we draw the free body diagram of the wedge first, and then the weight or the block or anything, any object, any body which is on top of the wedge, right? Because now we know the direction. Okay, so if you go back, so here you can see that and on top of this wedge, N2, the normal force is acting downwards, right? And F2 is acting parallel to the surface, acting leftwards, right? So now on this box at the bottom, you can see that N2, the normal force, will be acting upwards, right? And F2 is acting rightwards. Okay, so this is the normal force and this is the friction force. So the direction of this N2 and F2 will be opposite to the direction of these forces acting on the wedge. Okay, but their magnitudes are equal. That's why we have same notation N2 and F2 for these forces. Okay, and then this is the center of gravity of this block, at which this W or the weight of the block is acting. Okay, then if you go back, so the top block is also contacting the wall on the right side. Okay, so that's why we have on the right side the contact surface between the wall and the block, right? So from there also we have two forces acting on the right side of the block. So we have a normal force, this N3, and a friction force F3. Now this block is being lifted with the movement of the wedge, right? So this block is going up. So that's why this F3 is coming down. F3 is directed downwards, right? Because friction, this is a friction force, and friction force is always opposite. Okay, so that's about it about the free body diagram of the block. Okay, now once we are done with these free body diagrams, then we need to determine the unknowns. Maybe it's P, or maybe it's the weight, or anything which we want to determine, right? So we must apply equations of equilibrium, sigma fx equals to 0, sigma fy equals to 0, to the wedge and the object, as well as the frictional equations. Because if we have more unknowns, then we have to use friction equations. Okay, and we know this friction equation already, right? F equals mu s, which is the coefficient of static friction, times the normal force. Okay. Now, after we are done with the free body diagrams of the wedge and the weight or the object on top, from where shall we start the analysis? We should start analyzing the free body diagrams in which the number of unknowns are less or equal to the number of equations of equilibrium and frictional equations, right? So we need to see that. We need to see in which free body diagram we have lesser unknowns. So if you take a look here on this free body diagram of the wedge, so we have 1 unknown, 2 unknown, 3 unknown, 4th unknown, and 5th unknown. So we have 5 unknowns in this free body diagram. Now, if you take a look at the free body diagram of this, the weight on the top, or the box on the top of the wedge, we have 1, 2, 3, and 4 unknown, because weight, we know the weight, right? So this is not an unknown. So we have 4 unknowns in this system, right? In this free body diagram. Okay. So we have lesser unknowns in the free body diagram of the box, right? So that's why we should start with the free body diagram, start the analysis from the free body diagram of this block. Okay, so all right, so that was about the analysis of the wedge system. Now we'll quickly have a look at the analysis of the belt, right? How do we analyze a belt? Okay, as we know that we use belts to transmit the torque from a machine, from a motor, to any equipment. So let's say that this is a belt, right? This is a belt going over this curved surface, right? So this is your belt, right? So we have some tension here, we have some tension here. That's a T1 and T2. Okay, so consider this flat belt passing over a fixed curved surface with the total angle of contact equal to beta radians. All right, so this is your total angle of contact, right? This guy. This is your beta. Okay, so this is the total angle of contact between the belt and the surface. Now, if the belt slips or is just about to slip, then T2 must be larger than T1, right? So we all know that if T1 equals T2, then it will be static belt, right? There'll be no movement. But if one of these is greater than the other, T1 is greater than T2, or T2 is greater than T1, then we'll have some movement, right? So then the belt would slip over this surface. Okay, now to do the analysis, this is the equation which we use to relate T2 and T1, right? T2 equals T1 times E to the power mu times beta. Mu is the coefficient of static friction between the belt and the surface, and beta we already know. Beta is the total angle of contact between the two surfaces, right? So that's how this equation, we use this equation to do the analysis of the belt system, right? Okay, we are not going to go over problems for the belt analysis. We'll just do problems for the wedge systems, right? So this belt analysis was just to give you an introduction, just to tell you about the belt analysis and how do we do the belt analysis, and we use this equation to do the belt analysis. Okay, so with this, we come to the end of the theory part of this lecture, and now we'll go over to the handout, in which we have two problems involving different wedge systems. Okay, so this is problem 1 on your handout. Let's see what's given. Okay, so we have this system where we have this wedge A and wedge B. Okay, so we have two wedges. Now let's go to the statement. 3,000 pound load is applied to wedge B. Okay, so this is the 3,000 pound load which is applied to this wedge, wedge B. The coefficient of static friction between A and C and between B and D is 0.3. So we have so many contact surfaces, right? We have this contact surface, we have this contact surface, we have this contact surface. So we have 3 contact surfaces. Between A and C and B and D, we have 0.3 as coefficient of static friction. And between A and B, between the two wedges, the coefficient of static friction is 0.4. Okay. Assume the wedges have negligible weight. So we don't consider the weights of these wedges. We'll just consider this 3,000 pound load, this guy, which is being lifted from wedge A, right? Now, what do we need to find? We need to find the smallest force P needed to lift the 3,000 pounds load. Okay, so we need to find this guy, this force P, which is needed to lift the load of 3,000 pounds. Okay, so what are the steps? We already talked about the steps involved in the analysis of the wedge systems. So let's have a look again. Draw the free body diagrams of wedge A and wedge B. Apply the equations of equilibrium to wedge B and apply the equation of equilibrium to wedge A, right? Okay, so let's do these steps and let's solve this problem. Okay, so first of all, we will make the free body diagram of wedge A. Why wedge A? We already discussed about that. Why wedge A? Let's come back. Because we know the direction of move of wedge A, right? Because the force is being applied towards the right side, towards the positive x direction. So we know that the wedge A is moving towards the positive x direction, right? So that's why we'll start with the free body diagram of wedge A, because we know this direction of this force P, and we know the direction of move of this wedge A, right? Okay, so now we draw this outline sketch of this wedge, and now we need to apply the forces. So we know this guy, force P, so we apply this force, and then what else? Now we have two contact surfaces. One is between this wedge A and the ground, and one is between wedge A and wedge B, right? So now as this wedge A is moving to the right side, so where is the friction force, right? Friction force would be opposite to this direction of move, right? So this guy is the friction force, let's call it FC. And what is FC? We know it's mu s times NC. And what is the coefficient of static friction? It's 0.3, right? And this is the normal force, NC, between the ground and the wedge A, right? Acting perpendicular to the surface, right? So FC would be equal to 0.3 NC, and that's the friction force acting at the contact surface of the ground and wedge A, okay? Now, if you look at the top of wedge A, we have two forces, normal force and friction force, Okay, so again, the wedge A is moving to the right, so the friction force will be in this direction, right? The left direction, but it will be parallel to the surface, parallel to the contact surface between wedge A and wedge B, right? And similarly, this normal force, this guy, will be perpendicular to the surface, right? Normal to the surface. Okay, so now we know that this F equals 0.4 times N. 0.4 is the friction coefficient and N is the normal force, right? So now, how many unknowns do we have? Got 1, 2, 3, 4, and 5. So we got 5 unknowns in this free body diagram. Now come to the this free body diagram on the right, free body diagram of wedge B. Okay, so just draw the outline sketch and then apply the forces which are acting on this wedge B. Okay, so first of all, we have this 3,000 pound load on top of wedge B acting downward, right? So we apply this. Now we come to the bottom of the wedge B, and we have two forces, normal force and friction force. We already went through the theory that how do we apply this normal force and friction force, right? It will be equal and opposite to the forces acting on top of the bottom wedge, right? So if you look here, this guy N and this guy F, so we'll apply these but in opposite directions, right? So that's why this F will be in this direction. This is your F, the friction force, and this is your N, the normal force, acting opposite to what we have on top of wedge A, right? Okay. Now we have two other forces acting on this wedge B, right? Because if you go back, let's see, we have a contact surface between the wedge B and this wall D, this guy, right? So we have this contact surface. Okay, so that's why we have two forces acting on this surface of the wedge, on this side of the wedge. We have a normal force, this guy, let's call it N sub D, and we have F sub D, which is the friction force. Now, what is the direction of friction force? If you just visualize, we are moving the wedge, the bottom wedge to the right side to lift the wedge B upwards, right? So once the wedge B move upwards, so the friction force would act downwards. So that's why FD is acting downwards, right, in this direction. And ND is always opposite to the contact surface, and it's perpendicular to the surface, right? So that's why we have ND in this direction. This is your ND. Okay, so now we are done with the free body diagram of this wedge B. So let's see how many unknowns do we have. So we have 1, 2, 3, and 4. So we have 4 unknowns on this free body diagram of wedge B. Okay, so now we have to start the analysis. So from where shall we start the analysis of this system, right? So we already know, we went through the theory once we were doing the steps, that we need to start the analysis where we have the lesser unknowns, right? So in wedge B, we have lesser unknowns, we have 4 unknowns. So let's start from wedge B, okay? So apply the equations of equilibrium to wedge B. What do we get? So we know the equations of equilibrium by now. We have two equations, sigma f x equals to 0 and sigma f y equals to 0. Okay. So first apply sigma f x equals to 0 with the sign convention of rightward positive. Okay. So we are applying these equations to wedge B. So what are the forces acting in x direction? If you take a look at the free body diagram, we have the x component of F, we have the x component of the normal force, and we have N sub D, right? So we have three forces. So this is the x component of normal force at the bottom of wedge B. This is the x component of the friction force at the bottom of wedge B, and this is the normal force on the right side of wedge B, right? So we have these three forces acting on this wedge B in x direction. Next, we will use this sigma Fy equals to 0 with the sign convention of upward positive. So how many forces do we have in y direction? So we have four forces, right? So we have this guy and cosine of 15 degrees, which is the y component of normal force at the bottom of wedge B, right? Then we have this guy, which is the y component of the friction force acting at the bottom of the wedge B. Then we have this guy, which is the friction force acting on the right side of wedge B, right? And then we have this guy, negative 3,000 pounds, which is the weight to be lifted, right? Acting on top of wedge B, okay? So now we have these two equations, and if we solve these two equations, we can find out the value of n and value of nd, right? Because only these two are unknowns in these two equations, right? So we can find out n and we can find out n sub d. So n equals 4,485 pounds and nd equals 2,894 pounds. Okay, so with this, we are done with the analysis of wedge B because we wanted to find out n and nd, which we found out, and now we can apply the equations of equilibrium to wedge A. Okay, so now coming back to wedge A, so now we know this guy, this normal force from the analysis of wedge B, right? Because again, if you remember, the forces acting on the interface of the two wedges, they are equal and opposite, right? So we already know the direction, and now we got the magnitude. This guy, n equals 4,485 pounds, and this F equals 0.4 times normal force, so 0.4 times 4,485 pounds, right? So now we know these two forces, okay? So now how many unknowns do we have now, right? We have this n sub c, and we have this load P, right? So we are only left with two unknowns. So now we can apply the equations of equilibrium to wedge A. Let's apply sigma Fy equals to 0, which gives us this n sub c plus 0.4 times 4,485 pounds times sine of 15 degrees, which is the y component of this friction force, right? This guy. And then we have the y component of normal force acting on top of wedge A, right? This guy, which is acting downwards, so it's a negative, right? Equals to 0. So from here, we get n sub c equals 3,868 pounds. Okay, so now we got nc. Now the only thing we are left with is the load P, right? So let's do sigma fx equals to 0, and we can get the value of P from there. Okay, so how many forces are acting in the x direction? We have this guy P acting in the positive x direction, so it's a positive. Then we have this guy 0.3 times 3,868, which is the friction force acting at the bottom of wedge A, right? This guy 0.3 times nc. Okay, so it's a negative because it's acting in the negative x direction. Okay, then we have this guy, which is 4,485 times sine of 15. So this one is the x component of normal force on top of wedge A, right? And then we have this guy, 1,794 times cosine of 15, which is the x component of the friction force acting on top of wedge A. Okay, put that equals to 0, and from here everything is known except this load P, and we can get the value of this load P as 4,054 pounds. So that's what was required to find in this problem, and we were able to find this load P to lift the load of 3,000 pounds on top of wedge B, right? So if we apply this 4,054 pounds load on wedge A, we can move the 3,000 pounds load upward. Okay, so that's how we are done with this problem. Now let's do another problem. Let's do the second problem. Okay, so here, let's have a look here. This is the system given. We have this wedge A at the bottom at an angle of 10 degrees. So the surface is already inclined at the angle of 10 degrees, right? So we have this wedge, and this is the force P, which is being applied to this wedge A acting rightwards, right? And then we have this, let's say block B. This is block B, which is resting on top of wedge A, right? And then we have this spring on top of wedge B, right? So it's a little complicated system, but not to worry, we'll go through this, okay? A force P is applied to move wedge A to the right. The spring is compressed a distance of 175 millimeters, okay? The static friction coefficient is mu s equals 0.35 for all contacting surfaces, okay? Neglect the weight of A and B, so we don't need to consider the weights of wedge A and block B, right? We need to find the smallest force P needed to move wedge A, okay? So let's visualize this system. So we are applying this force P on this wedge A, okay? So to move this wedge A in this direction, positive x direction, okay? And with that action, we are trying to move this block B upwards, right? And then we have a spring on top of this block B, which is already being compressed a distance of 175 millimeters. Okay, so what's going on? We have this spring constant given, K equals 15 kilonewtons per meter. So once the spring is compressed, then it's putting some force on top of wedge B. Sorry, not wedge B, block B, right? So this spring is applying some force downwards on top of this block B, right? So we need to find that force first. So we'll find out that. And then we have some contact surfaces. The contact surface between wedge A and the ground, let's say. And then we have a contact surface between A and B. And then we have contact surface between block B and the rollers on the sides, right? Now, the important thing to note is that as we have rollers on the right and left side of this block B, so we don't have friction on right and left side of this block B, right? Okay, so the only friction forces are between block B and wedge A, and between wedge A and the ground surface. Okay, now we need to find the smallest force P needed to move the wedge A, right? Okay, so we know what are the steps. We just go through those steps. Okay, so draw the free body diagrams of the block and the wedge. Apply the equations of equilibrium to block B to find the friction force when the wedge is on the verge of moving. Then apply the equations of equilibrium to wedge A to find the smallest force needed to cause height. All right, so let's do that. Now, first step is to draw the free body diagram, right? So we know that we always draw the free body diagram of the bottom object first, right? So we have this wedge at the bottom. So let's have a look at this free body diagram of wedge A, right? So we draw this free body diagram of wedge A first. We know there's force P, which is acting towards right. So we know that the wedge is moving in positive x direction, right? So as the wedge A is moving in positive x direction, so we know that the friction force are acting opposite to the direction of motion, right? Direction of move. Okay, so this is the friction force at the bottom of wedge A, between the bottom surface of wedge A and the ground surface, right? So let's call it F sub A. So this is your F sub A, which equals 0.35, which is the coefficient of static friction, times N sub A, which is the normal force, right? Now this FA is parallel to the surface, right? Now N sub A is perpendicular to the surface. So this is your N sub A, right? Acting perpendicular to the surface or normal to the surface. Okay. So now we are done with the bottom of the this wedge A. Now let's look at the top of the wedge A. What forces do we have? Right. So as we already know that the wedge A is moving to the right, so we have this F sub B friction force acting to the left, right, opposite to the direction of move. Okay, and this is the normal force N sub B acting perpendicular to the surface, right? So now FB would be equal to 0.35 times N sub B, mu S times N sub B. Okay, so now we are done with the free body diagram of wedge A. Now let's see how many unknowns do we have. NA, FA, FB, NB, and force P. So we have 5 unknowns in the free body diagram of wedge A. Now after we are done with the free body diagram of this wedge A, now let's go to the block B and find out how many unknowns after drawing the free body diagrams. Okay, so this is your block B on top of the wedge. Okay, so first of all, let's find the spring force. We know that the spring force equals K times X, right? K is the spring constant, X is the displacement, right? Compression or extension. Okay, so we just multiply the spring constant, which was 15, times 0.175, which is the compression in the spring, which gives us 2.625 kilonewtons as the spring force acting on top of the block B acting downwards, right? So this is your, let's say, FSP, force due to spring. Okay, so we are done with the top surface of the block B. Now let's discuss about the right side. So on the right side, and we have the rollers, right? So we don't have friction. Okay, so we don't have friction on this right contact surface between the block and the rollers. So that's why we only have this N sub C, which is the normal force acting on the block, right, from that contact. Okay, and there's no friction force. All right, now let's come to the bottom. On the bottom, we have 2 forces, normal force and friction force. Now, what is the direction and magnitude of this normal force and friction force? We know that it's equal and opposite to what is acting on top of the wedge, right? So we have FB acting to the left on top of wedge A, right? So on the bottom of block B, we'll have FB acting towards the right. And the magnitude would be same, 0.35 times normal force, N sub B, right? And N sub B would be equal and opposite to the N sub B, which is acting on top of wedge A, right? So N sub B would be acting upwards and the magnitude would be same as what we have on top of wedge A. Okay, so with this we are done with the free body diagram of this block B. Now let's see how many unknowns do we have. So we have this NC, we have NB, and that's it. So we have only two unknowns in this, right? Okay, so we have two unknowns in this block B. Okay, so this is using the spring formula. This is just the explanation of how we get to the spring force, which is K times X. 15 kilonewtons per meter is the spring constant, and 0.175 meter is the displacement or compression in the spring. So we get 2.625 kilonewtons, which is the force acting from the spring to the top of the block B acting downwards. Okay, so after that, now from where shall we start? We should start from block B, right? Because we have only two unknowns in block B. Okay. Another important thing, if the wedge is on the verge of moving to the right, then slipping will have to occur at both contact surfaces, right? So that's why we can use FA equals mu s times NA and FB equals 0.35 NB, right? Which we already draw on the free body diagram. Okay, so after we are done with these two free body diagrams, then we can apply our equations of equilibrium to these free body diagrams. So again, as we discussed, from where shall we start? We should start with the free body diagram of block B, because we have lesser unknowns over there, right? So let's apply sigma Fy equals to 0 with the sign convention of upward positive. Now, how many forces do we have in y direction? So we have this spring force, and we have this N sub B, right? So we'll have NB minus 2.625 equals to 0. So from here, we can just straight away find out what is N sub B. So NB equals 2.625 kilonewtons. Acting upwards, so it's positive. Okay, so that's what we wanted to find from this. Now we can move to wedge A, right? Because now we have the value of this NB, N sub B, and due to that, we can find out this guy, and we can find out this guy. FB equals 0.35 times 2.625, and this is NB itself. So now, how many unknowns are we left with in the free body diagram of wedge A? We are left with NA, and we are left with P. Okay, so we are left with two unknowns. So we can just apply the equation of equilibrium to wedge A. Let's apply sigma Fy equals to 0. How many forces do we have in y direction? We have three forces, right? We have 2.625 kilonewtons acting downwards on top of wedge A, right? So this is negative 2.625. Then we have the y component of N sub A and y component of F sub A, right? So this is the y component of N sub A, and this is the y component of F sub A. So from here, we can get the value of N sub A, which is 2.841 kilonewtons, right? So after applying this equation, now we are only left with force P. Okay, so let's apply sigma Fx equals to 0 with the sign convention of rightward positive. Now, how many forces do we have in x direction? We have four forces, right? We have FB, we have the x component of FA, the x component of NA, and we have force P, right? So everything is known except force P, right? So we'll write down this equation, sigma Fx equals to 0, and we can find out what is the value of P from this equation, which is 2.39 kilonewtons. Okay, so that's how we are done with this problem, doing the force analysis of this wedge system. Okay, So that's how we found this force P, which is required to move this wedge A with the block B at the top. All right. Okay, so this is the end of today's lecture, and see you in the next lecture. Thank you.